Today we're going to continue the systems component of our series by talking about distributed file systems. Specifically, we're going to talk about NFS, which is a traditional POSIX file system that is extended over the network. And then we're going to talk about Google's file system, GFS, and how this was sort of specifically engineered to work with distributed systems as opposed to end users, and what this engineering trade-off sort of means in terms of how it's actually implemented. So, as a brief review of what is a file system, we think at a basic level, we're trying to do something to store information. And it's going to be layered on top of a lower level device, like a hard drive, that doesn't really impose very much meaning on top of what you write out to it. And what is going to make this different from a database, for example, is how we interact with the data. So in a database, we'd have a series of tables, and new data elements are entered as a set of rows. And each row is then divided into a bunch of columns, which each has its own semantic meaning to the database. And the database itself can interact in a column-wise manner with this data. In a file system, however, data is obviously just stored in files. And we only really have one thing that we can associate with that file, which is a name. And then so we can map from names to some large chunk of data, but organization within that is then left up to the actual client of the data itself. The external system doesn't really impose any structure on that. The one thing that we do impose on a regular file system, though, is this notion of a hierarchy. Files live in either folders in the Windows world or directories in the Unix world, which can conceptually just be thought of as namespaces. So we can have the same name associated with multiple pieces of data if they live in separate namespaces. And the way that we actually address these namespaces is through a path, which tells us which namespaces inside of one another we are accessing in order to get to the particular file. And of course, these paths can exist in two forms. They can either be relative to some current working directory, or they can be absolute, which actually provides a complete path from some designated root of the file system. But of course, this is a distributed course, so we're talking primarily about how file systems would be extended to the distributed setting. And in distributed computing, as we've figured out, there's a lot of data that needs to get sent to multiple machines. So we're left with this choice where we could either design our own protocols to transfer data to the different machines that are doing computation for us, or we could latch onto an existing mechanism and use that abstraction to provide our data in multiple places. So file systems are an abstraction that are already going to be there in whatever support system we have to build our programs. So if only we could just make our file system do the heavy lifting of getting the data to multiple machines, then this would be a win for us from the distributed computing point of view, because we won't have to implement any protocols on top of this. So distributed file systems are designed to present just this ability, and they don't actually make, and what separates a distributed file system from a regular file system is that they don't actually make any claims about how the data is being stored. They're a higher level file system which gets layered on top of an existing file system. And the distributed file system just presents an API that allows the data to be accessible over the network. And of course, a distributed file system is going to need to provide a number of guarantees that would be inherent to any distributed system. For example, concurrency is obviously the biggest of these. Multiple machines, multiple distributed computing components have to be able to access the data at once. And when we have concurrency, we have to figure out how do we lock files across a distributed network, how do we cope with latency in the locking or with concurrent writes, and how do we make sure that if individual components of our network crash or otherwise become disconnected, what happens to these locks, and how can the rest of the system proceed in the face of these partial failures? And of course, speed and bandwidth minimization are also going to be important. So replication of data can be built into one of these file systems to provide faster local access, and local caching will cut down on redundant bandwidth usage. But of course, each of these are going to come with complexity trade-offs in how we're going to actually build this and keep all these local copies consistent with one another. So what we're going to do now is look at two different file systems, NFS and GFS, as I said, and NFS being the most well-known and ubiquitous distributed system, and then we'll talk about GFS by way of comparison. So NFS was first developed in the early 1980s by Sun Microsystems, and the architecture goal of NFS was to be as unsurprising and Unix-like as possible. NFS can support pretty much everything that a full POSIX file system can. POSIX is the acronym given to a set of standardizations that are implemented by a number of Unices over time. So the initial design goal of NFS was that if you have a bunch of users on a network, like here at Google, then when you log into any terminal, your files should be available from that machine. They shouldn't be stored on the hard drive of one particular computer. They should be stored deep somewhere in the central server room and then relayed out to whatever end terminal you happen to find yourself sitting at. And they didn't want you to have to use any special interface to access NFS. The directories that NFS exposes should interact transparently with the existing directories on the physical file system of the machine you're at. So an interesting thing about NFS was just how dumb it was initially designed to be. The entire protocol started out entirely stateless, which is to say that after you made a request, the server didn't log any information about that request. You make a request, it gives you data back of some kind, and then from its perspective, the request is in the past and never will refer back to it again. So there are commands like, give me this portion of this file, or I have data to write into a file, or can you tell me the list of files in this directory? But doing this didn't actually have any locking or anything built on top of it. You would have to use a separate higher level protocol out of band to actually provide things like exclusive access to files. So remember 2 lectures ago, I mentioned that there are 2 protocols that are used a lot on the internet, TCP and IP. To reinforce how stateless NFS was, they actually did not even use TCP/IP. They used a separate protocol called UDP/IP. And whereas TCP has the concept of a connection to another machine and, like I said, sequence numbers to keep track of what order the data is coming in, UDP does nothing of this sort. It simply blasts data packets down, and if they get dropped in the middle, the other machine will never know it. And there's no concept of a persistent connection. It's, oh, data has arrived. So all of these different clients are coming in effectively through one pipe to the server, and they don't have their separate broken out streams. So over the last few years, we've realized that the added overhead of putting TCP connections into this actually does make it simpler in the long run to add things like locking and other useful protocols. But this is seriously as of like 2001, whereas it had been running for well over 15 years in this completely stateless mode. So as I mentioned a few slides back, a network file system doesn't necessarily have anything to do with the actual local file system. So for this reason, NFS is often referred to as a virtual file system. The files are actually recorded on the disk using either Riser or ext or whatever other concrete file system the user chooses. And NFS is only going to define how you expose these files to the outside world and how the client and the server interact. And in fact, since the NFS server sits on top of the user visible file system of the server itself, it's possible to have more NFS clients built down into the file system view that it exposes, and you can have like a daisy chain of multiple machines being aggregated like that. Obviously, the files eventually have to terminate in some concrete file system somewhere, but nothing prevents them from being at least 2 hops away because of how the NFS client transparently fits in with the existing concrete file systems on a machine. So in the picture here, we see that we have a client computer and a server computer. And if the client wants to access files in some directory, it might go down through this real file system here, or they might just be exposed by this NFS client, which masquerades as a real file system. And anytime you ask for any of these files, it's going to send a network request over to the server, who then fills in the actual data itself. So as we've seen whenever I brought up concurrency, concurrent accesses are going to need locks associated with them. So how the file system does locking is important to keeping everything coherent. So clients will either request locks from the server and it will grant them, or else it will tell the client that some other client has the lock already. It doesn't block on the server side. It sends a message back to the client telling it that it should lock. Or, I'm sorry, it should block. And so, of course, this raises the question, what happens if a client dies while it holds the exclusive lock to a file? And the way NFS solved this is by a lease-based mechanism. So it says, when you have a lock, I'm giving you this lock, but only for the next 5 minutes. And after, say, 4 minutes, your client will then ask the server to extend the lease for an additional 5 minutes. Or else it will just finish its changes up and release the lock. However, if a client crashes, then the lease will time out, and the next client to ask for one will be given permission. As I said earlier also, we'd like to minimize bandwidth usage within a file system, so they support a caching mechanism so that if you request the same file twice, you don't have to read the whole contents of the file out from the server 2 times. However, what happens then again if we have concurrent accesses going on? If we have a copy of a file, we have to know if some other client has modified the server's copy. And where we arrange these accesses can affect how we actually do the synchronization. So, for example, one way that we could have done the synchronization is by having some callback associated in the local file system. And then anytime a change is made on a foreign machine, the NFS server could then tell the local system, oh, by the way, there are changes to your cached copy. However, as I said, NFS is a stateless protocol. So the NFS server doesn't actually remember that you've opened the file. So therefore, it can't really give you a callback. So the trade-off that they made with NFS was a system they called closed-to-open cache consistency, which means that changes to a file are only manifested to cached clients after that file is closed. So if we have 2 clients, A and B, and A has opened a file, it opens it for this chunk of time and then closes it. If it then opens it again, we're going to use the cached copy here. If in the meantime, we open the same file here, so it's in the middle of this current transaction with it, and we make some writes, these writes are not going to be shown to this view of the file. It's only the next time, here's a close, and here's an open. All of the changes that occur in this transaction are only going to be shown there. So when we reopen the file, we ask the NFS server, did anybody else update a copy? And it will say, yes, here's the new copy to use. But this existing transaction sees this one serialized after it. And if we want to have two clients that are modifying the same file and actually sharing data through it, then they have to open the file with a special flag set indicating that cached copies should not be made. So a couple other trade-offs that they made with NFS was that a single NFS volume can only be managed by a single server. You cannot have a federation of machines that are all responsible for the same directory tree. And so while this places a higher load on the central machine, because all of the writes need to be reflected back through exactly one computer, it simplifies the coherency protocols a lot. Because with the single machine doing the writing, we don't have to have any distributed lock aggregation or a vote to determine who actually gets to make the write. And the other trade-off is that by adding the full POSIX system, they can drop it in anywhere, and no programs need to be updated to take advantage of it. You can write a program that runs all on one computer and push it out on multiple computers without any changes to the file layer. But of course, by making it general, that means it is not particularly well suited to any individual task. So now that we've talked about a standard network file system, we'd like to take a look at how Google implemented theirs. And whereas NFS was developed with the end users and regular applications in mind, Google file system only works with large distributed applications, and end users don't usually need to directly manipulate the file system, say by running programs like ls. So the motivation behind their design goals was that they needed a file system that can redundantly store data across cheap and unreliable computers. So if any one machine in the system fails, it should be transparent to the actual client applications of this system. And of course, the amount of data that they have is going to be very large. And like we said, an existing file system is going to be sort of geared either to different priorities or it's going to be very generalized. Whereas this one, since it's the same people designing both the file system and the applications that run on it, they can get a tighter integration and push different things into either the application or the file system level as they see fit. So some assumptions they made about the workload in their system was that the individual components are going to fail a lot. They use regular commodity hard drives, not particularly specially engineered ones. In fact, a study recently showed that even if you buy the more expensive hard drives, they don't tend to fail that much less than the regular commodity ones that you'd buy off the shelf in a regular desktop. So since components are going to fail anyway, you have to design your system to just embrace it. Another point is that when you design a file system, there are a number of different corners you can optimize into. Reading, for example, can be optimized at the expense of writing because you can put all of the writes to a file in the same place in the file system. So that means that you might have to move data around when writing, which is slower, but the reads will go quick because the data is all next to each other. If you had more writers than readers, though, you might just want to always write to the end of the file system, which means that reads are going to be fragmented, but writes are going to be very fast. So the files that they use are going to be large streaming reads. You're not going to need to jump around in the file. We want to read through files in order and usually bring out large chunks of several hundred megabytes at a time. Each of these files is also going to be several hundred megabytes, and there are not going to be very many tiny files. So there's no reason to store tiny files compactly in this system like you might need to on an end user's machine that has a lot of 2 and 10 kilobyte files lying around. And whereas regular file systems also have to deal with potentially billions of individual files, their file system is only going to be holding a few million at a time. So it doesn't need to be able to scale out the file table itself very large. And as a final point on this, because we're going to be doing streaming reads, it doesn't matter really how fast the initial bytes from a file get to us, because once we've started selecting a location to read from, we're going to continue to read straight through for a while. So the throughput matters far more than the latency. So the design decisions that were made based on these assumptions was that the files should be stored as large chunks. Whereas on an end user's file system, files might be stored in 4 kilobyte or 8 kilobyte blocks, Google decided to up this by a factor of 10,000 or so and make it 64 megabyte blocks as the minimum addressable unit. So that definitely makes the streaming much easier across a whole 64 megabyte segment. They also decided that since individual components are going to fail randomly, the way that they should ensure that the system is reliable is by replicating the data across many machines. And each chunk, as a large piece of the file is referred to as, is replicated across at least 3 machines in the system, which are individually referred to as chunk servers. They also decided that all of the metadata should be kept on a single master machine, which will be then coordinating access to the individual chunk servers from the clients. And because the data sets are so large and they're going to be streamed every time, there's not a particular incentive to allow user-side caching. Because if you cached one file that's a gigabyte, well, then where's your next file going to go? It's probably going to need to overwrite it anyway. So you might as well get rid of caching in the first place and then not need to build that complexity into the system. And finally, they decided that the interface should be familiar. It should look similar to a POSIX system, but there's no terrific incentive to make it exactly POSIX-like. So since they've decided that they can go stray a bit from the POSIX functions, that allows them to add their own functions that they find particularly useful. For example, there's a lot of writes to the end of a file that occur in the Google file system. So they added a particular function called record append, which allows them to atomically add an element to the end of a file very quickly. Another function they added is called snapshot. So this is a picture, a diagram of the architecture of the system. And you can see that the applications talk first to this master server about where to get the data from, and then the actual bulk of the data, which is through this thicker line, comes directly from the chunk servers itself. The master keeps track of a table that maps file names in the hierarchy to a set of chunk IDs and the servers that have them on it. So a client will ask the master, where is such and such a file, and it will give them back that set of locations. The client will then pick one of those locations randomly and give it the handle to that chunk, and then the data comes straight back from the chunk server. So whereas in NFS, all of the reads had to come from this one computer, now the reads are not bottlenecked through this one choke point. Can anybody spot a potential weakness with this design, though? In the back. What do you do if the master server goes down? Right. So from the design paper we read on the first day, we know that this is a single point of failure and a scalability bottleneck. So the solution to the single point of failure problem was to create other machines which were called shadow masters. And whereas there's only one master at any given point in time, it is periodically sending copies of its metadata down to these other computers, which can then keep that in the event of the initial master failing. They can swoop in and say, we have a pretty recent copy of the file system and still can start mapping chunks to chunk servers. And from the scalability point of view, they decided that as long as the master did not need to send very much data at a time, it would not be a scalability bottleneck very much. So the chunks are very large, which means that there are a relatively few number of chunks per file. So when accessing a file's metadata on the chunk server, it doesn't need to give it some megabyte long list of chunk servers. It just has to send them out 20 or so integers, and that's the locations. The data mutations are also all handled by the chunk servers, not the master itself. So its involvement is continually kept quick. So like I said, the principal job of the master is to store the global metadata, which is the file and chunk namespaces and the mappings of the files to chunks. And another way that they keep the master's scalability high is by keeping this entire table in RAM, because it comes out to being only 64 bytes of storage per chunk, which, if you think about having even 20 million files or so, that's really only going to be 200 megabytes, which is easily kept in the RAM of one computer. The other piece of metadata kept on the master computer is an operations log, which is persistent on the disk, not just in memory. And this is actually replicated through the shadows, so that to keep it able to recover quickly and to ensure consistent data. So, can anybody see why it's important to log the information on the master? So with chunk servers, we have multiple machines which are all holding the data. So if one of these machines gets totally corrupted, we're allowed to just give up on that machine, because we know we have two other copies somewhere. But as I said, we only have one copy of the master. So if we were going to do a set of mutations to the master, like modify two different values to hold x and y, for example, if we only wrote out x and we didn't write y to the disk, then all of a sudden our single master copy of the metadata is corrupted. So the way they handle this is by having a separate list of things they're going to write before they actually write it. And so you have some log entries that say start, and then you'd say we're going to write x, then we're going to write y, and then there's some special end token. And you write this out to disk, and then you actually write your data in. And if we crash halfway through this process, then we can just read the whole log. And if we crash halfway through this process, we'll realize that we don't have that special word end there, and we can treat it as though it never happened. And since this never happened, none of those writes ever happened, and the true copy will always stay intact at some version. It might not be the latest version. However, by having a consistent view, we can then replay some writes onto it later, knowing that our previous writes can't be corrupted by future ones. So mutations are the thing where it gets really complicated to have multiple copies of data lying around. We have a master, we say, oh, there are these 3 chunk servers with your chunk. If you want to read off of it, that's easy. You just pick one and go, right? And because we know they're all consistent. But how do we keep them consistent if we actually want to change them? We have to change them all at the same time with respect to any other concurrent accesses. And as I said earlier, because we only have one master machine, we need to minimize its involvement in this process. And the way that they handle this, again, is through some leasing mechanism. So when we want to write to the master server, when we want to write to some file, we ask the master server, where are the chunk servers for this? And we tell it we want to open this for write. At this point, the master is going to designate one of these copies as the primary copy. And then we are going to tell the primary copy what we are going to write to where. The primary copy then tells the secondary copies where these mutations need to be made. So in slightly more detail, I can show this out on the board. Suppose we have some file named foo, and we want to write to 3 different chunks of this file. And they can be 1, 3, and 5. We have at least 3 chunk servers for this file. So we ask the master, who are the chunk servers for this file? And it gives us back their information. One of these chunk servers is told that it's the primary server. At this point, the client does 2 things in parallel. The dark arrows running down the center show the data flow. And so the client will send the actual bytes for these chunks, the 64 megabyte blocks, to one of the replicas. It doesn't care which. And they will figure out what are the other replicas for the same file and send them along their way. We then tell the primary replica we want to change these. And assuming that we call this guy client A, it's going to start formulating a change list that has this information in it. When the data has arrived at all of the replicas and they notify the primary replica that the data is ready, the master will tell them what order, based on this list that the master replica is creating, to swap them in. That way, if we had some concurrent write by machine B, which wanted to say write to 2 and 3, they would be given the same primary copy, because the primary copy has a lease on the file for as long as it's undergoing some mutations. So because they have the same primary copy, they would have to send these commands to the same server, who would necessarily put them at the end of the list. Then because this same list is being propagated to the other replicas, what we would end up having is this would win, this would win, this would win, and because this is later, this would overwrite that. And now all of these replicas are going to have the same copy of the data. It's not possible for some of them to see the write by A and some of them to see the write by B, because there was one replica that was coordinating the whole process. And obviously, reads that occur during the middle of a mutation are going to get directed to the primary copy, who is going to illustrate that in the middle too. Question in the back.
When is the file considered written? When all of the servers, chunk servers have gotten the new data propagated to them, or when only one of them has gotten the new data?
All of the replicas must receive copies of the data, and they must then tell the. I'm sorry. The question is, when is the data said to be written? When one server gets it, or when all of them get it, and the data has to. The 64 megabyte chunks have to reach all of the replicas for that file, and then the primary replica. Then and only then will the primary replica tell them to actually make the changes, and then it will notify the master that it can yield its lease back. The other style of mutation that they provide is this atomic record append operation. And the reason that they add this is because rewriting the entire file is not usually something that gets done very often in a GFS client. But what Google does use their file system for is a lot of logging. There are programs which are being run on all of their servers that are consistently checking all sorts of statistics, like how much is the incoming and outgoing bandwidth, how much CPU is being used. And they write all of this out to the file system in large tables. And so we want to make it convenient to just write a small snippet to a file. So therefore, Google provides an atomic record append operation which guarantees that each record is added at least once. And this means that all of the data in the record is going to appear together. It's never going to be interleaved with data from some other record. So if we have two records, one of which is represented by brown and one of which is green, concurrent writes of this record and this record will appear side by side, but we don't guarantee the order between replicas. So whereas one replica may see this, another replica may see that. And it's also possible, due to various timing inconsistencies, to get the same record twice. So any systems which make use of this atomic record append operation need to have validation internally so that they don't count duplicates. The one thing the file system does guarantee, though, is that a situation where the individual pieces of a record are not actually interleaved like so. So when we're discussing how files are presented to users, we want the file system view to be something which is consistent, which would mean that all of the replicas have the same value on them. Regardless of which chunk server we pick, then we should be able to get the same total file back. And defined means that not only are all of the replicas consistent, it means that a mutation actually happened. So when we talk about failure, we have to ask what sort of consistency is actually guaranteed by the system. And if we have concurrent writes, this is going to leave the region consistent, which means that all of the replicas will have the same value, but it might be undefined. So if we have concurrent writes, the writes might knock each other out. However, they're definitely going to knock each other out across all replicas. It will never partially get through. That having been said, if one of the chunk servers comes back and says that it failed, then the region is inconsistent, which means it might be possible in that case to have all of the chunk servers inconsistent for a file, and you would need to go back and rewrite it if the write function actually returned failure. So this actually moves some work into the applications themselves of if they get back an error condition from the write function, they need to then go back and rewrite the whole file. So having a full consistency model with multiple concurrent readers and writers and multiple copies of the data is a lot to deal with, especially in the face of failures. Consider, for example, if we're running MapReduce on this. We've already talked about how MapReduce continually restarts machines and runs things in parallel, etc. And if we have to keep track of locks in all of this case, then it would start getting really complicated because the individual mappers can't even see each other when asking for these locks. So the way they handle this is by having this relaxed consistency that allows them to cope with these failures. And because they know about the particular applications running on this file system, they can deal with it. The important thing to keep in mind, however, is that all of the metadata is at all times both consistent and defined. And that's because of the operations log that we showed earlier. So all of the namespace operations, like actually creating and deleting files, renaming them, are guaranteed to be both atomic and serializable, which means that there's an order to them based on how the actual locks are acquired. So what does the master server actually need to do, since we've shown how much of this work is actually pushed off to the chunk servers themselves? And as I said, it's responsible for metadata storage, it's also the only machine that's actually going to be doing all of the locking. So whereas we say that we have leases in the chunk servers, those leases are only granted through the master. A chunk server can't promote itself to being the primary on its own without permission from this master. It also is responsible for maintaining track of the sort of global health of the cluster. So it's periodically pinging all of the servers and making sure that they come back. And if servers start timing out, it decides to write them off as failed. It also gives other instructions to the chunk servers. For example, if one chunk server crashes, then since the master knows all of the files that were on that server, it will then start directing other servers to make copies of them to keep the number of replicas at or above the safe replication threshold. Another thing is that because there's only one master, that machine knows exactly how many reads and writes are being made to each file. So if the master starts seeing that there are dozens and dozens of read requests from separate clients coming to different machines, it can tell or to the same file, it can start telling different machines to replicate that file so that we can provide faster throughput to the individual clients in these sort of hotspot cases. Another thing that the master does is garbage collection. Whereas on a regular file system, you want to delete files principally because you want to free up space for more files. In the Google file system, they've already got several hundred machines tied together with absolute terabytes of storage. So the concept of running out of space and needing to delete files to make room doesn't make as much sense as it does in your home directory. So instead, the way that they actually do file deletes is that files are deleted from the namespace by renaming them to some random hidden name. And then periodically, when the rest of the server is not terribly busy, then it will go through and actually physically remove the chunks that are associated with these files. Also, like I said earlier, failed writes can leave regions undefined but consistent, which means that there might be old versions of chunks that are just sort of left abandoned on individual chunk servers. And all of the chunks are given a version number throughout the writing process, and the master asks periodically each chunk server which versions of files it has. And if one chunk server disagrees with the other two copies, it will go through later and then direct it to remove that old copy and get a fresh one. So it is eventually self-healing in this regard. And finally, what's the bottom line on all of this? They've created a very fault-tolerant system that manages huge amounts of data in the face of all sorts of system failures. In particular, they've made a very high availability server cluster. The machines can restart very quickly. Individual servers can be rebooted in a few seconds. Shadow masters can fail over from the main server within some very short timeout window. So even if several different applications start to stall, within a minute they can have things running on a backup copy that might not necessarily be 100% up to date, but can still keep 98% of the data from the previous iterations of files. And even if 2 out of every 3 machines were to die, assuming that files were distributed randomly properly, all of the files should still be intact in this case. Finally, they've also added additional layers of reliability on top of the basic hard drives themselves. The chunk servers individually hash elements of files and are checking files they read against these checksums that they've presumably stored on a second disk. And if a chunk server detects that it itself is failing, it can vote itself out of the server and direct other replicas to take over responsibility for the files that it has and make those files available again on machines which are not self-diagnosing problems. Of course, not only does this system work very stably, it wouldn't really be scalable to thousands of clients if, in fact, it wasn't very fast. So the table on this slide is taken from the paper, and it shows 2 different actual clusters used here in Google. And they both have several hundred servers, 342 and 227 each. And it shows that they have a lot of disk space actually being occupied by files on these clusters. There are a lot of numbers up here, but I think that the 2 things that are important to note are that 1, the amount of metadata is extremely small, given how much of the actual real data is there. It's well under 1%. And the amount of data that the master needs to actually keep in its RAM is extremely small and will probably pretty easily fit there. The second thing that's important to take away from this table is that the transfer rates are actually pretty good. The peak read performance is 1.3 gigabits per second, which will saturate the line coming out of a small to medium data center, and is clearly actually keeping up with the amount of traffic that it's being requested to handle. So how's it actually being used in Google? Well, as of 2003, there were at least 50 clusters being employed, each of which can have up to a couple thousand storage nodes and actual petabytes of data, which is pretty big to think about. And GFS is the system that they use underneath of other systems here at Google, one of which is called Bigtable. As I mentioned earlier, there's all this logging operation. That's actually going into this Bigtable structure, which creates a distributed database system layered on top of the Google file system. So to conclude, GFS demonstrates how to support large-scale processing workloads on commodity hardware. The design is shown to tolerate frequent commodity component failures, and that it's scalable, especially for the particular design goals in the system, like huge files that are mostly appended and primarily read and not very often rewritten. It's also shown that as long as you have control over both the applications and the file system, it's possible to make some engineering shortcuts for simplicity that relax the consistency model and extend the file system interface in interesting ways by providing operations that would not normally be available in POSIX or in another particular file system that you would pull off the shelf. And sometimes it shows that simple solutions, like just having a single master, are actually good enough in enterprise-scale deployment, as long as you know how to actually harness it down so that you can keep the workload on those machines minimal. Sometimes having a single machine in a distributed system with a particular job isn't necessarily such a critically bad thing. And it's been meeting Google's storage needs, so it must be good, right? So the next lecture, which will not be in very long, we're going to start learning about algorithms for distributed computing that are useful in distributed applications. And we're going to start by talking about some clustering algorithms. Any questions on GFS? Yes?
I have two questions. Are all the chunks associated with the file always on the same set of chunk servers, or as I'm reading a file, would I have to change chunk servers? And the second question is, how do the shadow and the master share the operational log? How's that synchronization?
The first question is, are all of the chunks for a particular file stored on the same chunk server, or the same set of chunk servers? I don't necessarily believe this is the case. I don't remember off the top of my head. My hunch would be no, because if you want to have high availability for particular sections of a file, like say a dozen clients all start reading the first 500 megabytes of a 3 gig file, it would be very inefficient to have to replicate 3 gigs 10 times across the GFS network. You probably only want to replicate the actual hotspot segment of a file. The second question, sorry, can you say it again?
How's the communication done between the shadow master and the master? The operational log?
The second question is, how is the operations log shared between the master and the shadow masters? The operations log, I believe, is written out to disk on the master, and then at some delayed time, I believe it's sent to the shadow masters. So I believe the shadow masters can actually be a few seconds behind the master in what is the most up-to-date metadata. So if the master were to crash and it fails over, it might be that the last few seconds worth of writes are not actually reflected in what the system knows about. You'd have to check the paper to be 100% sure, though. Other questions? Any from abroad? OK. In that case, let's take a break for about 15 minutes, and then we'll come back and have a lecture on clustering. Bye, Sierra.